So let's take a look at more examples here. And we did some last time. So let's see. And so consider let's say if we start from scratch with this set, consider this set, all right, of course, where, I is the imaginary or the imaginary numbers. So that I squared is -1. Is this a group? Is this a ring? And so we'll check. So for a group, remember, we want to check CIIA. And we're again, we're going to do addition and multiplication. So for the group, we'll consider addition. So C, remember, is closed. So the question is, if we take, say, two typical ones, say, R1I plus R2I, then that's going to, and when we add them together, that's going to end up being like R1 plus R2I. And of course, that's going to be of the same form as we started with. So therefore, because we have like a real number times I, so that would be in the set. So that would be closed. And identity. And of course, 0 is going to be in the set. So we have an identity. And then the inverse. So given a typical RI, does it have an inverse? So the inverse of, say, a typical RI would, of course, be negative RI. And since R's can be all real numbers, if R would, negative R would certainly be in the set. So we're going to have an inverse. Again, because then RI plus a minus RI is 0. So we have an inverse. Then associativity, if we take, like, say, if we say take three typical elements, R1I, R2I, R3I. If we added these two together, that would give us R1 plus R2I plus R3I. And that's going to be equal to R1 plus R2 plus R3I. And the question is that the same as if we added these two first and put that on? R1I plus R2I, R3I. So if we start with this, that'll give us R1I plus R2 plus R3I, and add them together. Like this. So if we added these two first, add this one, and we would get this, or if we added these two first and then added this one, we still get the same thing. So it is associative. So then this set is a group. So this is a group under addition because it has these three properties. It's closed under addition, identity, inverse, associative. And then the second question is a ring. And as of course, on the handout, I sort of called this ACAD. So it has to be in a billion group. And actually, a billion group, remember, just means that you can commute the values. And of course, you can commute real numbers. So it's a group, and it's also in a billion group. Real numbers and complex numbers, for that matter, always commute. And so we also need to check for closure under the second operation. So again, our second operation is going to be a multiplication. So now if we take two typicals elements, so once again, let's check for closure. So if we take two typical elements, R1I, R2I, and if we multiplied those two together, we would get R1, R2, I squared. And of course, I squared is -1, so we get R1, R2, like that, huh? So actually, it looks like it's not closed, is it? Because we don't have, we multiplied these two together, we did not get something in this form. We have like Ri. So, we could have R be 0, so it'd be okay if we had 0 here. But in this case, if we take two typical R1I and R2I that aren't 0, we're going to get this. So this is not in our original set. So it's not closed. And so it's not a ring. Any questions on that? That would be one, just if you're starting, say, right from the start and trying to calculate, to determine if something was a group or a ring. So always remember, of course, that CIIA is for a group and ACAD is for a ring, or you might have your own way of memorizing those things. And again, if we know something is a subset of a ring or a group, we could use the subset or subgroup test. And let's see. Do a couple others here. Let's do this one here. Let's say if we take 2 by 2 matrices first of all, let's take this particular form. So these are 2x2 matrices. And they're in particular this form that this is always going to be the same as this. And I won't go through quite as slowly this time. So let's go through. Is this a group under matrix multiplication? And is it a ring? Excuse me, matrix addition. Yeah, sorry. Matrix addition. And that'll be our first operation. Is this a group under matrix addition? And is it a ring where the second operation is matrix multiplication? And so let's take a look at this. Again, maybe we'll go through quite as slowly this time. Again, closure, I think we can see it's closed. If you pick two typical matrices, let's say two like that, and you add them together, remember you add them together component by component. Now notice that the form that we need is for the upper left to be the same as the lower right, and that's true. We need the lower left to be 0, and that's true. And we need the upper right, really can be anything. So it looks like it is closed because we picked two typical elements, added them together, and still got an element in the set. And so identity, of course, is just going to be 0, 0, 0. And that's going to be in the set because we could have A0 and B0. And let's see, how about inverse? If you took a typical A, B, 0, A, inverse is going to be negative A, negative B, 0, negative A. Looks like that would work. And associativity, I won't go through, but that's going to work. Because the associativity is really based on the fact that the real numbers are going to be associated because we're just associating them when we add the matrix. So this is a group under matrix addition. And then the next question is, so is it a ring under multiplication? And so let's take, first of all, let's check for closure. If we multiply two typical elements, A1, B1, 0, A1, A2, B2, 0, A2. If we multiply these two together, remember what it is. It's going to be this row times this column, and that'll be A1, A2 plus 0, because it can be 0 times that, so it's going to be A1, A2. Then there's going to be this row times this column, A1, B2, we take this one times this one, then B1, A2. Then we multiply this out, we're gonna have A2 times 0, A1 times 0, so that's gonna be 0 plus 0, that's gonna be 0. Then finally, we're gonna have, this one's gonna be 0 plus A1, A2. And it looks like we got an element that's in the set, huh? Because we have the 0 in the lower left. We have the upper left and the lower right being the same. Then this one could be anything. So it looks like it is, this one is closed. Now let's see. The next question would be, is this a commutative ring? So let's see if it, excuse me, there's some other things we have to do, sorry. We have to do, associativity, and we also, yeah, we have to do associativity, then we have to also do a distribution. So let's see if we were to do A1, B1, 0, A1, excuse me, A2, B2, 0, A2. If we were to multiply these two together and then multiply this, so let's say we multiply these two together first, which we did up here. That's going to give us A1, A2, 0, A1, B2, plus B1, A2, A1, A2, times A3, B3, 0, A3. And then if we were to multiply these two together, and I think I'm going to run out of room here, so I better just go ahead and go to the next page. So if we multiply these out, this is going to give us A1, A2, A3. That'll be this times this plus this times this, so it's going to be plus 0. Now we're going to take this one times that one. Plus this one times that one. And then this one times that, which is 0, plus this times that, which is 0. Then this one times this one. And then finally, so that's the one way. So let's try it the other way. Let's try A1, B1, 0, A1. Excuse me, that should be A2. B2, 0, A2. A3, B3, 0, A3. So multiply these two together first. And that's going to give us, remember, it's going to be this row times this column. So it'll be A2, A3 plus 0. this one, A2, B3 plus B2, A3. Then down here, 0 plus 0. 0, this would be A2, A3, like this. And finally, this times this is going to be A1, A2, A3, and then plus 0. Then this times this is going to be A1, A2, B3 plus A1, B2, A3 plus B1, A2, A3. If we take this one times this, it's going to be 0 plus 0. This times this is going to be A1, A2, A3. And so let's check to be sure we got the same thing. Of course, this is the same. This is the same. A1, A2. This is the same here. This is the same here. So it looks like it is associative. And I won't go through it. It's also distributive. The distributive laws hold. So this is a ring. And the next question is it a commutative ring? So we said, let's see, we already calculated it one way. Let's calculate the other way. So the question is a commutative ring. So let's say if we do A2, B2, 0, A2. Hopefully you can get all that in. And then A1, B1, 0, A1. So this is going to be A1, A2 plus 0. This is going to be A2, B1 plus A1, B2. This is going to be 0. This is going to be A1, A2. And so let's see what we had before. When we multiplied these two the other way. We multiplied these this way and got this. And now let's see what we have. We have we have A2 B1, whereas before we had A2 B1, and then we have A1 B2, so those match, and we have A1 A2, A1 A2. Again, because real numbers commute, then we can say that A2 B1 is the same as B1 A2. So it looks like they do commute because we did it in general. So this is a commutative ring. And let's see what else. Let's see what else we need. So the question is, do we have an identity? And of course, the answers. So the question, we have to have an identity of the form that we were given. So remember our form here, we need an identity that's in this form where upper left and lower right same. And of course, we're gonna have that because 1, 0, 0, 1, that's the identity. If you remember from matrices, anytime you multiply something with this form, that will give you the matrix back. So the identity is there. And let's think of what else do we need. So we have identity. And the other question is every element a unit? So and again, if you haven't had linear algebra, yeah, I wouldn't expect you to remember this, but if you have, like, say, a typical matrix A, and you have A, B, 0, A, then remember the determinant of A is going to be A times A minus 0 times B. In this case, it's going to be A squared. And the A inverse is going to be, remember we switched these two. And change the sign on these two. And then divide by 1 over this. And so this is going to be 1 over A minus B, 0, 1 over A when we multiply these out. And so again, remember, every non-zero element has to have an identity. How about this one? Do you think, is that going to work for every non-zero element? Or what one? I hear no. I hear some no's. I think no is the correct answer. Because of course, if it's non zero, that the would include, so this won't have an inverse, huh? If we were to do something like maybe this, huh? It looks like that wouldn't have an inverse because then our A squared would end up being 0. So we would have 1 over A like that. In other words, so in this case here, A is 0. And so when we tried to find its inverse, it would be undefined because 1 over A would be undefined. So no inverse. And the other question is, so let's see, how about zero divisors? So again, we determined it's let's see, so what did we determine? It's not a division ring. It does have an identity. It does commute. It's not a division ring because not every element is a unit. How about zero divisors? Now, in general, matrices have zero divisors. Trying to think. So in this case here, so we have, do we have two? So if we have, like, let's say, if we took something, So if we did this, let's say if we multiply these up, this would be 0. Multiply this time, that'd be 0. And this is going to be, if I'm looking at that right, that'd be 0 as well, huh? And then that's going to be 0. It looks like it has 0 divisors, huh? If I'm looking at that right, because we multiply, this would be 0 plus 0, and then 0 plus 0. Yeah, so we took two non-zero elements and got 0. So it looks like we have 0 divisors. So it's not an integral domain, because the integral domain would have to have no 0 divisors. It would have to, there couldn't be any two elements, so when you multiplied them, you would get 0. So would we determine then, we just have a, I guess, so this is, we determine we have a commutative ring with identity, huh? But we didn't have an integral domain, and we didn't have a division ring, and certainly we don't have a field. Again, I realized a lot of you didn't have linear algebra, but it was kind of this was kind of an example where you could kind of bring a lot of this stuff in. So, but again, you don't have to know stuff about matrices if you didn't have linear algebra. Any question on that? Any questions at all? Yeah, a lot of these other examples I have are well, one thing, as I mentioned before, we were doing, if you remember back when we did like subgroups, again, this is I think this is worth doing for rings as well. And we can even do it for fields later. Actually, let me do it for fields first. Again, this comes up a lot in math. It's a pretty simple proof. We did this for groups. Now let's do this for fields as well. Suppose S and T are subfields. Prove that S intersection T is a subfield. And so, and just to remind you, remember the subfield test was for all A and B. I may use different letters before in like say the in the set that A minus B is in the set. And would we say before for all A and B in the set, we have A, B inverse is in the set. That was our subfield test that we mentioned a couple days ago. Again, this is what's nice about this. Again, using these tests, you only have to test a couple things. If you know something is a subset of a field, then you just have to use these tests. Let's take a look at this. So in this case, we have two subfields already. We want to prove that they're intersections of the subfield. Again, the process is the same. anytime you do these intersection type problems, again, they come up lots and lots of times in math, and the process is always the same. So again, we want to pick two typical elements in this set and then prove these things. So let A and B be in this in our intersection. And then since S is so therefore, and let me go through all the steps just to make it really clear. So we're gonna let this happen. And again, want to prove we want to prove that this is going to be true. So let this be true, then A is in S, excuse me, AB is in S, and AB is in T by the property of the intersection. And then since S and T are subfields, and therefore they're fields themselves, bank A's are subfields, we're going to have that A minus B is in S, and A minus B is in T. Again, that's because we know that S and T are subfields, therefore they have to have passed this subfield test. So if you have any two elements in that are in S, their difference is going to be in S. Those elements are in T, the difference is going to be in T. And then therefore, if they're both in S and T, A minus B is going to be in the intersection. So we passed the first test. We picked two typical elements in the set and prove that their difference was in the set. In this case, we picked two elements in ST in the intersection and prove their differences in the intersection. And then let's do the second test that we have to do here. You wouldn't have to write let again, but I'm going to just do it just for completeness. So let S and T, A and B be in S intersection T. Again, one of the things for the test, I didn't write it up here, was that B is not 0. And we're going to assume B is not 0. Then again, A and B are in S, and A and B are in T. But since S and T are subfields, then that means that they both will have had to obey the subfield test, which means for any two elements that are in the set, A, B inverse is going to be in the set, and A, B inverse is in this set, like that. And since they're both, this is in S, this is in T, therefore AB inverse is in this intersection, like that. So once again, we picked two typical elements in the set we were interested in, S intersection T, and prove that AB inverse was in the set. And so that, along with this, we passed the two subfield tests. So S intersection T is a subfield. Which again, remember, just like with groups, if something's a subgroup, it means it's a group itself. If something's a subfield, it means it's a field itself. It just happens to mean just the fact that we have this, we know that it's a subfield. We just know it happens to be a subset of another field. Any question on that? Again, that's a proof that in lots of different forms comes up all the time. So it's something good to be aware of. And let's also, then like I said, we're going to have an exam a week from Friday. I haven't given you much homework, so maybe for your homework, I mean, you don't have to turn this in, but use your normal homework time to study for the exam. I'll give you all the practice problems. For this one here, so for the quotient group, think about what we have for this. So remember what the quotient group is. So if we have something like this, that's coming from Z15. And so remember, if you have something like this, all the quotient group is, so think of what 6, this is a cyclic group. And to remember, you'll get the elements from this by starting with 6. 6 plus 6 is 12. 6 by 12 is, plus 12 is 18. But mod 15, that's going to be 3. And then 3 plus 6 is 9. Then 6 plus 9 is 15, which is going to go be 0. So then what we're going to have is going to be 0, 3, 6, 9, 12. So that's going to be, and then remember your quotient groups are simply taking each one of these and adding numbers from the group to them. So this is going to be like 1, 4, 7, 10, 13. Add 2 to it. 2, 5, 8, 11, 14. Oh, I'm already done, aren't I? So I can stop there because the next one's just going to be a repeat of that one. So that's your quotient group right there, these elements. So this quotient group here is just made up of these elements. And remember, the elements are these sets. Remember, the subset itself is the identity, huh? And again, remember with these groups, it's like this is so the quotient group has 3 members, this set, and this set. Remember, when you have a quotient group, the sets become the members. And so this is your group right here. And then also the order, what is the order of this element? Remember to find the order, keep adding it together until you get the identity. Remember to find order, keep adding until you get the identity. And now, so in other words, let's add this one together And you'll find this out. You really can just add one element of the group together, and that's all we really need to do. But I'll go through the whole thing. So let's say if we added this together, add it to itself, this would be 4 plus 10. Then 16 is going to be 1. 22 is going to be what, 7? And then 28 will be 13. So that's not the identity. So let's add it to itself 3 times. We'll take that one. And add it to itself again. So I'll add this again. So it's going to be 6. 15 is going to be 0. And then 9. Let's see, 18, which is going to be 3. And then, be sure I don't mess it up, that's going to be 27, which is 12. And that looks like the identity, huh? I just have them in different order, but that's the identity up here. So identity. And so I had to do that, what, 3 times. So the order is 3. And once again, if you want to take a shortcut, you could take any element and add it to itself and a number of times till you got something in the identity, huh? In other words, we could have just added 2 to itself twice and got 4 and seen that wasn't in the identity, then add it to itself again to get 6. But that was the identity. You could take any of those numbers, you could take them 5, add it to itself 3 times, you'll get something in the identity. So if you want to take a shortcut, I usually don't emphasize that because sometimes people get confused about that, but you could just take one element in the set and keep adding to it to itself till you got something in the identity. But so there you go, those are pretty easy. The same thing for the next one, you do the same thing, just see how many times you have to add it together to get the identity. So a lot of the things on these practice problems here are not too difficult. So any questions on anything?